Hello everyone, I'm Frank and welcome to Frank Puzzles, and this is today's easy level other type puzzle, and it's specifically an Ichikara puzzle. Today's puzzle is called Aperture, which is an Ichikara puzzle by Michael Lefkowitz. And here are the rules. We have Ichikara, where we need to divide the grid into regions. A region contains the numbers from 1 to n once each, where n is the largest number in the region. And regions may contain empty cells, and a question mark stands for any number. So we need to divide the grid into regions. And each region contains the numbers from 1 to n, with n being the largest number, once each. So you could have a region here of 1, 2, 3, 6. You would need 4. Say the largest digit here was 7. You could technically have this be a region because it has the digits 1 through 7 exactly once each. What you could not have, though, is this be a region because these are the digits 2 through 7, but we don't have a 1. So remember, every region must contain the numbers from 1 to its highest digit once each. And those are all the rules. Again, a question mark can stand for any number, and regions may also contain empty cells. So that's why this can work here. Anyways, those are all the rules. If you'd like to play along, there's going to be a link in the description. And now, I'm going to get started. Let's go. Okay, what I like doing with Ichikara puzzles is counting the number of digits we have total, and that does not include usually the question mark. And that will tell us how many possible, what the each region's largest number can be. So we have 2 8s here, we have 2 7s here, and 2 6s. That means we are guaranteed there are 2 regions that must have 8 as the largest number, at least. You could have another one having 9 as the largest number also. We have 3 5s, so that means at least one region. So we have 2 regions, obviously, which require the digits 1 through 8, at least. That means you have an extra 5 here. We have 3 4s, we have 3 3s, we have 4 2s, and we have 4 1s. So what can this extra digit be? Can obviously be a 1, because we have all the higher digits are less than or equal to all the digits below them, right? So there's 2 8s, there are also 2 7s, 2 6s, 3 5s, but we also have 3 4s, 3 3s, 4 2s, and 4 1s. What this digit could be is a 1. It cannot be a 2. If it were 2, we would have to have another 1 be able to go with each of the 2s, but that would be 5 2s and 4 1s, which obviously doesn't work. You could have a 3 here, because 3, that would make 4 3s. We'd have 4 2s available and 4 1s available, so that could work. You cannot have a 4 or a 5, because if we had, that would make 4 5s or 4 4s, but we would only have 3 3s if this were a 4 or a 5. And this could be 6. It cannot be 7 or 8, because, again, we only have 2 6s available, 2 7s available, and 2 8s available. But this could actually also be a 9. We actually don't know. Anyways, the 8 has to be in the 8s have to be in the same regions as the 7s and the 6s. Though we could have an extra 6 here. But each 8 has to belong to a 7 somewhere. And this 8 cannot be in the same region as this 7. If it were, the problem is, so these regions have to orthogonally connect to each other. And by this orthogonally connecting, it would block the other 8 from connecting to the other 7. So we know these are the same region, and these have to be the same region here. Similarly, this red region cannot orthogonally connect to this 6. Because if it connects to this 6, the problem is that it would block the blue from connecting orthogonally to form a region. So one of these is going to be red. This could be blue, or one of these could be blue. We don't know which. Blue has to get to one of these 3. Okay. Um, hmm. 5 has to be one of these 3. Hmm. Though 6 has to access one of these 3. Okay, what happens if this is not blue? If we try to... this can't be 6. If this is 6, the problem is you would have to orthogonally connect with the reds, and that would block these 2 corners from being together. So this must be a 6 here to match. And the blue has to go around this red 6. Because if it can't, if this 6 is going to have to orthogonally connect to this 7 either this way or this way. Either way, it has to get around this blue has to get around this red connection. And it's always going to be here. So therefore, to get around, you're going to have to go this way. Which means you have guaranteed here this is blue. This cannot be blue. So this must contain, and we have a 4 here. This 6 is going to have to be a different region, and it needs access to a 5. We already have a 4 for the blue, so that eliminates 4. We need a 5 for the blue. Red at least is going to have to go there. Blue at least is going to have to go there. At minimum, right? Because blue cannot block the orange from a 5. And if it goes this, connects this way, it will block the orange from a 5. So blue is guaranteed at least to go this way. Red is guaranteed at least to go... I guess blue could go something like here. Red could go something like there. But blue doesn't actually have to go there. In fact, it can't. So if red goes here, if blue tries to go this way, it's blocked by this 4. So blue's going to have to do something like this. And orange needs access to a 5. So blue can... Blue... Yeah, blue definitely has to go something along these lines here. Cannot do this. Well, could do that. Don't really know. But basically, 6 needs access to a 5. If it goes that way, it's going to block blue from orthogonally connecting to the rest of the blues. So this cannot be the orange 5. And if we try to connect this way to this 5, that will block again the blues from orthogonally connecting to this 8 here. So this must be orange that way. which means blue has to go, blue can't go this way, blue has to go around here, and then it has to go all the way around this orange. So it must orthogonally connected from here to here, and then from here to here. Orange needs access to a 4. It cannot go here because that blocks the blue from orthogonally connecting to the other blue. Because blue has to go this way. So the only 4 it can access is here. So this is orange going that way. That's 4. Blue has to go this way to connect to the 8. So that's the 5. So this cannot be blue here. Which means of the 5s, this must be red. So blue has to go this way to orthogonally connect. Red has to go this way to orthogonally connect. Blue could do some sort of stuff here. We don't really know. Red has to go this way to orthogonally connect, so this can't be red here, so it must go red there. Blue has to go this way to orthogonally connect. So we know these are boundaries. The boundary this way. This has to be boundary. This could be 2 for blue. We don't know. Orange needs a 1. It needs a 3. It needs... Okay. So this blue cannot connect with this 3. So it must go that way. Because we already have a 3 there. Orange then has to go this way, which is a 1. Which means it cannot intersect to any of the ones here. So it must connect going this way. So this is 2, 3. This is obviously boundary. This must go this way for orange. Blue has to go this way because there's no other way to orthogonally connect. Orange has to go this way at least. Blue has to go here. This 3 needs access to a 1, so it has to be with this one. That means blue has to go this way. Blue has to go here. Blue must go there. Pink has to go this way. Orange must orthogonally connect. So we have boundary here. Boundary here. Red needs access to... Ooh. Oh, this pink is the same as red. So this is red. So we have to orthogonally connect. We need access. We already have 1, 2, 3, 4. This 2 needs access to a 1. Or this 2 needs access to a 1. This 2 cannot access a 1 except... If it tries to access a 1 here, it will block... If it's not part of the blue region, I should say, it will block the blue region from connecting. So this must be part of the blue region. That means red has to go there. These have to be part of the same region. That means blue has to go down this way. Red has to orthogonally connect that way, so blue has to orthogonally connect that way. So that's done there. Blue has to orthogonally connect. This is done as a region. Blue has to orthogonally connect here. Red has to orthogonally connect here. Blue must orthogonally connect down here to connect to there. And this must be red orthogonally connected. Yeah, I'm not sure how to solve this puzzle for... I don't know. Do we put 8s for everything that's there? And 6s? And we have 8s here? Nope, that doesn't work. I don't even know. Oops. Maybe the problem is this has to be 6. No. I don't know how they solve it though. Anyways, this is the solution. So this red region has 1, 2, 3, 4, 5, 6, 7, 8. This blue region has 1, 2, 3, 4, 5, 6, 7, 8. The orange region has 1, 2, 3, 4, 5, 6, and the pink region has 1 and 2. And that's how you solve it. Yep, fairly straightforward. I've gotten really good at looking at orthogonally connected regions, and that's what Ichikara really does. It's very similar to chaos construction in a sense, in that you have to come up with these puzzles or these regions to bound digits from 1 through 9. So, anyways, I hope you enjoyed this solve, and I'll see you next time on Frank Puzzles. Take care.